So, till now, for this last class or today, you are unable to see anything on the laptop, correct? You are to just listen. So this thing I will give you later. The problem is with respect to my laptop. Everything was in my laptop, so I was able to copy it. So after in coming week, I will be able to give it. You will be able to get full note. Okay. By this time, I am talking repeatedly that you go through the IS 456. Frequently, you go to the IS 56 because this paper or in your future life also, you will be required to utilize this IS 456. Okay, I will just read how to solve a problem of so day before yesterday we had defined one slab, we had defined slab, one slab normally, one slab or so having support on two opposite edges and the support is normally in longer direction. And second condition was the sheet slab is having measurable two dimension, two plane. Third dimension is very small, length and breadth. Length and breadth. These two are measurable, but the depth, D or capital D, whatever you mention, it is compared to very small, very small. Okay. Now a slab may be supported. A slab may be supported on all four edges. Under that situation, what will be how we will get this slab is one way. So for that, on last day also I told you, the longer length to shorter length ratio, if happens to be greater than 2, then if at all the slab is supported on all four edges, still the slab is one slab. This condition. Now only under this condition, if the slab is supported on all four edges, the spanning will be in which direction? The spanning will be on shorter direction. In structural analysis, this was not deduced. Now it was in deflection. In deflection, the deflection of a slab in both at midpoint, with respect to both directions, so longer direction as well as shorter direction, must be equal. So from that condition, it will be observed that as Ly by Lx approaches or going to 2, numerically to 2, the load transpired with respect to longer span reduces and load transpired with respect to shorter span increases. And it is observed that when longer span to shorter span ratio is 2, with respect to shorter span, load transferred is out of total load, the small w, 95% of the total load is carried by the shorter span. Only 5% load is carried by the long span. Okay. So under this situation, moment, although it is supported along shorter direction also, the moment is only with respect to 5%, so it should be negligible. So that's why moment with respect to short span is neglected and moment with respect to short span is considered. Now suppose we are having a slab. Since we need the effect of shorter direction, the longer direction effect we need not consider. Suppose we are given that we are given that a slab is there The effective span is 3.5 meter. Length, whatever it may be, it is immaterial. Length is immaterial. And the load acting to be acting on this slab is given, and say the load acting, whatever I solved the problem, 2 kilonewton per meters, 2 kilonewton per meter square, 2 kilonewton per meter square, including self weight. Including self weight, so where to design it? So very simple, this is just similar to design of beam. Only a small difference is there. So in this problem, our effective length is given. Effective length is 3.5 meter. Intensity of load is 2 kilonewton per meter square. 2 kilonewton per meter square. So I told in our last class itself that when we are to design a slab, we always consider which B is 1 meter. B is 1 meter. In case of beam, B may be 200 millimeter, 250 millimeter, 230 millimeter, 270 millimeter, 300 millimeter, and so on. But in case of slab, B is considered 1 meter. That means this slab along the lengthwise direction is considered 1 meter, 1 meter, 1 meter. Are you able to see my hand? Anybody say, are you able to see my hand?
Yes, sir.
In case of slab, you just see my movement. You see my movement. So this is the slab. So this is longitudinal dimension. This is breadth dimensions. So we have to take span in this direction. Whatever problem I am going to discuss, this dimension is 3.5 meter. And intensity of load is 2 kilonewton per meter square. It is acting here. Okay. So what we will consider? So this is 1 meter. Next 1 meter. Next 1 meter. Next 1 meter, and so on. Along the lengthwise direction, this slab is divided into strip of 1 meter, 1 meter, 1 meter, 1 meter, and so on. So we are going to design 1 meter width of the slab. So our load, it is inclusive self weight. So load is known. So what we are to give here a statement considering 1 meter width of the slab along the lengthwise direction. Along the lengthwise direction. So under that situation, also ultimately what happened? It is converted to a beam. It is converted to a beam whose span is 3.5 meter, which is 1 meter. Now we are interested to find out the depth. We have to find out the depth. Okay. So in beam design, with respect to deflection criteria, one condition was given that L by D, capital length divided by effective depth should not be more than 20. Should not be more than 20. But in case of slab, this is slightly modified. Length divided by overall depth. In case of beam, length divided by effective depth. In case of slab, length divided by overall depth. So for a simply supported slab, the same condition is valid. The same condition is valid, 20. But width is more, we can increase this value. So practically, this L by D ratio value, L by D ratio value for simply supported or one-way slab is considered from 25 to 30. From 25 to 30. So here let us consider length divided by overall depth is equal to 25. So our length is 3.5. 3.5, so 25, so 3500 divided by 25, so this is 160. Sorry, 140. So we got 140 overall depth. Now again from our code that I had gave you, the clear cover. So clear cover, let us consider clear cover minimum 20. And let us assume the diameter of the rod. The diameter may be considered 8 mm, 10 mm, 12 mm, and so on. Let us try. We will utilize 8 mm. We don't know whether 8 mm will be possible or not. We don't know. Finally, we will find out. So we got overall depth 140, clear cover 20, diameter of the rod 8 mm. So we can find out effective depth available. So effective depth available is equal to overall depth minus half T diameter of the rod minus clear cover. Our overall depth is 140. Diameter is 8, so 4 minus 20, so 140 minus 24, it is 116. This is available effective depth. Now whether this available depth is sufficient or not, that we have to find out. Now here our condition, we had got in our beam design 3 conditions. Under reinforced, over reinforced, under reinforced, over reinforced, and critical. So critical is the suitable. We are not allowed to go for over reinforced. We are not allowed to go for over reinforced. So critical. So let us see what will be the critical effective depth. So critical effective depth is equal to, we had mu, we got mu, we were able to bending moment, WL square by 8, it was 3.0625. Then we were able to find out factored moment 1.5 partial safety factor multiplied by maximum moment. So ultimately we had got factored moment 4.6. Then we had one expression. We had one expression for critical section. Mu is equal to 0.138 FCK BD square. So D is equal to mu by 0.138 FCK times B whole thing under root. Now here B is 1000. Mu we got. So from this we got D available, D required. From this we got D required 40.8. Our D available is 116. For critical section, this. So effective depth available is more than critical, more than effective depth required. Effective depth available 116. Effective depth required is 40.8. So it is safe. So what we have this condition that we have discussed here also, if D required is greater than D available is greater than D required, then the section can be designed as singly reinforced. The section can be designed as singly reinforced. So this we got. Okay. Now then we have to find out. So effective depth. That means slab thickness is finalized. Slab thickness is finalized. Slab thickness is 140 millimeter. Effective depth is 116. Now we have to find out the amount of steel. So for getting amount of steel, we require actual neutral axis depth and critical neutral axis depth. So critical neutral axis depth is 0.48 times effective depth. So 0.48 times effective depth is equal to, we got some value we will get 55.68. We require actual neutral axis depth. So for this, I had given one expression at the time of analysis. In note also you are getting, but this expression very rare people are utilizing. They are going from expression, then they are trying to find out a quadratic equation, then try to find out this. So here we are to getting, so that this expression is XU, actual neutral axis depth, is equal to 1.2 minus under root 1.44 minus, I'm sorry, 1.132 bracket 1.2 1.4 minus under root into mu divided by FCKBD square whole thing bracket D. This expression you have, yes, in your beam design. So here put all the values. We got D, actual neutral axis depth, we got very small, 5.64. So actual neutral axis depth is less than critical neutral axis depth. Okay, so it is under reinforced section. See, previously we had defined whether this section can be designed as single reinforced or double reinforced. So there we had got single reinforced. Now we establish that the actual neutral axis is less than critical neutral axis, under reinforced. The section is under reinforced. This says in steel attains its limiting value, but stays in concrete does not attain its limiting value. It is less than limiting value. Okay, so taking help of this, we got this. Then very simple, area of steel required. Area of steel required. We had one expression. Mu is equal to 0.87 Fy AST D effective depth minus 0.42 XU. So we know all the values except AST. So we got AST. We got AST. So area of steel it is 112 millimeters square. But for slab, according to clause 26.5211, we have to provide minimum amount of steel. So we are going to utilize torch steel. So minimum amount of steel is equal to 12% of cross section. So 12% of cross section means 0.0012 multiplied by B multiplied by D. So 0.0012 multiplied by 1000 multiplied by 140. So we had got 168. That means, although from theoretical point of view we require 116, 112 millimeters square, we have to provide 168 millimeters square. The higher amount of steel we have to provide. Higher amount of steel we have provided. Okay, so steel required we had calculated. Then we have to require the spacing. So spacing is equal to this expression you had not got. I am giving you spacing is equal to area of diameter of rod considered multiplied by 1 meter divided by area of steel, because this amount of steel 168 is required for 1 meter width. For 1 meter width. For 1 meter width. We can find out number also. 168 diameter of rod is 8. Then area of 8 mm diameter is 56 millimeter square. So if you divide 168 by 56, you will get a number. That much number of rod will will be equal to 8.1. Not much. Otherwise, we have to find out the spacing. For getting spacing, we will be able to find out spacing is equal to area of diameter of rod considered multiplied by 1000 divided by area of steel required. So from this I got 393 millimeters, sometimes 393 millimeters. Okay, now this we got. But the same is not attached to this light. So IS 456 gives some specification for spacing. The clause 26.3.3.B.1. Remember 26.3.3.B.1. It specifies that minimum that the spacing should not be smaller. Spacing should not be less than smaller of the following. One condition is 3 times effective depth. Second condition is 300 millimeter. Third condition is spacing whichever that is required with respect to design. The spacing to be provided should not be more than smaller of the plane. So this available in the code. So if you see 3 times effective depth, so 3 into 116, 3 into 116, so this happens to be 348. Second condition is 300, and third condition as per required, and as per required power is 333. That means the spacing of steel cannot be more than 300. Cannot be more than 300. Now it is up to you. Up to you individually. You can give any type of, you can give any spacing, but it cannot be more than 300. Cannot be more than 300. Say I am giving, probably I have given 200 mm. Yes. So I am giving, let us use a torque at the rate of 200, and if I give at the rate of 200, then I am going to provide amount of steel 224 millimeters square. See, from a structural analysis point of view, we have required 112 millimeters square. From minimum restriction point of view, we are supposed to give 168 millimeters square, and now I am giving 224 millimeters square. So you can give, I am giving 200 millimeters square, you can give 250, but it cannot be more than 300. Okay, so this amount of steel is provided along the span. Now along the longitudinal direction also will be, because in case of slab, the steel should behave as a mesh. So steel should be provided in both the directions. Now in longitudinal direction, the steel is provided not taking any expression, just from the code. So that steel is called distribution steel, or called this temperature steel. So this steel is normally minimum steel. That means minimum steel, that means 0.12% of the area. So 0.12% of the area we have 160 millimeters square. Okay, so for 100 millimeters, what is the spacing required? We can calculate. So what is the spacing required? We can calculate. But what we do? Already we have utilized 100 millimeters square. So better not increase. So let us utilize. Let us use the steel in both the direction. Steel in both the direction. Direction 7. Okay. So we have utilized the steel in both the direction. Again, you see my hand. Are you able to see my hand? Are you able to see my hand? Hello?
Yes, sir.
Yes. So this, see, why I am showing two hands. My right hand, I am giving this forefinger, just as an example, this is the main steel along the span, that means along the 3 meter, 3.5 meter. The fingers that I show just above this finger is the distribution steel. That means these steels are distribution steel, these steels are coming along the longitudinal direction. Okay, now, so this completes the design. The steel we had provided, just like beam. In beam, we had provided steel, main steel along the longitudinal direction and steel ups. Here, the main direction rod is given, and replacing the steel up, we are giving the distribution steel. Now, problem is coming. In beam, also, we had set one thing, deflection. So here also, from bending moment point of view, it may be safe, but there may be excessive deflection. Still, the structure, the slab will be safe, but it will be uncomfortable. The same procedure, whatever we have utilized for sake of deflection, the same procedure we have to apply. So for this, we have to find out the, first of all, we have to find out what is the percentage of steel we had provided. What is the percentage of steel we had provided? That PT, percentage of steel, that is PT, I had got. We had provided AST, we had provided, I think I had some mistake. No. No. So 280 divided by 1000 divided by 116, so 0.24. Now, in your note, one expression was there, Fs is equal to 0.58 Fy into at numerator area of steel required divided by area of steel provided. So that we have to find out area of steel required was 102. 112. Area of steel required was 112. Sorry, 168 minimum we have to give. And area of steel we had provided 280. So from this we had got one factor 0.24. Now I had given one table, one graph, figure 4. Figure 4 and figure 5. So from that we'll be able to find out there are 5 curves. At bottom it was the percentage of steel. Vertically it is modification factor. So percentage of steel known to us. Go vertically, you will be able to locate the Fs value. So parallel to the curve, you go at a point it will be, go to horizontally, you will be able to find out one modification factor. Okay. Now for this we had got modification factor K1 is equal to 2. K1 is equal to, now K2 second curve. Second curve, for second there is no compression steel. There is no compression steel, so percentage of steel is 0. So when percentage of steel is 0, this modification factor is 1. Second curve. So now our basic L by D ratio, considering as a simply supported structure, it is 20, that according to code. So the L by D ratio up to which we can go. So for that, the expression is basic L by D ratio multiplied by modification factor with respect to tensile steel multiplied by modification factor with respect to compression steel. That means L by D basic multiplied by K1 multiplied by K2. L by D basic is 20 multiplied by 2, it is 40. That means we can go L by D ratio up to 40. L by D ratio up to 40. But we had utilized L by D ratio 25. L by D ratio 25. So our structure is safe. So this completes the design of one step. Very simple.